Okay, our topic today is concentration of solutions. And after today's lesson, today's video, what you should be able to do is write the equation for expressing molarity. You should also be able to calculate the concentration in units of molarity for a solution, calculate the concentration of ions in solution with ionic compounds, and calculate the mass and or volume of reagents needed to prepare a solution of a given molarity. And you will also be able to define what a standard solution is. In order to perform chemical calculations involving solutions, we need to know two things. We need to know what is the reaction that is occurring, and we also need to know the amounts of the chemicals in the solutions. We describe number one with chemical formulas and balanced chemical equations. So that part is represented symbolically. For number two, what we've used before for amounts are usually in grams because we can, especially with dry materials, we can just put it on a balance. But if it's in solution, which we're going to see quite a bit in here, the amounts are expressed in concentration. And the unit for concentration is molarity. And that's a new term. The understanding of concentration and molarity is really important, so that's what we're going to talk about for the rest of our time here. Most reactions take place in solution, so therefore we have to know how much of each chemical we're really working with, and this is the concentration. For the formula that I need to write, molarity equals moles of solute divided by liters of solution. And I can abbreviate that using a capital M. And we can underline it for good measure because that will set it apart from other letters later on. So capital M equals moles, MOL, over liters, capital L for liters. Let's quickly review the definitions of solvent, solute, and solution. So a solvent, remember, is the substance dissolving another substance, and usually that's water. We talked previously about why water is such an important solvent. A solute is the substance being dissolved. A solution is the resulting homogeneous mixture of both the solvent and solute. So let's look a little bit generally at what concentration means. So a 1 molar solution would consist of 1 mole of solute dissolved in 1 liter of solution. I'm just using simple numbers here to get the concept across. A 6 molar solution would consist of 6 moles of solute dissolved in 1 liter of solution. It's fair to say that because I have more solute in the 6 molar solution than in the 1 molar solution, and my volumes are the same, that the 6 molar solution is more concentrated. And that's an important idea to come across, is the more concentrated something is, the more solute is dissolved in that solution. So what if I don't have 1 mole or 1 liter of solution? Well, I could still calculate the molarity using the conversions and using this formula that we just showed you. So let's do an example. I want to calculate the molarity of a solution prepared by dissolving 11.5 grams of solid sodium hydroxide in enough water to make 1.50 liters of solution. List out what I know. I know a mass. My mass is 11.5 grams of sodium hydroxide. My volume is 1.50 liters. Now, pay attention to my units here. My mass is given to me in grams, and so I'm going to have to convert grams into moles, and we know how to do that. So 11.5 grams, let's convert that into moles, and we're going to use molar mass here. Molar mass of sodium hydroxide is 40 grams, 40.00 grams. That's going to go on the bottom, and 1 mole is going to go on the top. When I divide these two, I get 0.288 moles of sodium hydroxide. Now that's the right unit that I'm looking for. I have a volume in liters, I have amount of solute in moles, so now I can put them into my molarity equation. 0.288 moles of NaOH divided by 1.50 liters of solution. And when I divide those two things, I get 0.192 molar NaOH. Alright, so that's the concentration of my solution. It's really important, again, to check over your units. We emphasize this in this problem, so if my units are not the same, I'm going to need to convert to make them fit into my formula. Here we go. Let's look at another example. Example 2. I want to make a standard solution of potassium carbonate. What does that mean? A standard solution is a solution in which you know its concentration precisely. So specifically, I want to make 250 milliliters of a 3.00 molar standard solution of potassium carbonate. What mass of potassium carbonate do I need to make this solution? So let's write down what we know again. We know we have a volume of 250 milliliters, and we know the concentration is 3.00 molar. I am being asked to find mass. Recognizing that we have concentration, we have volume, we're going to use our relationship that we learned earlier, so molarity equals moles over volume. Since we know molarity and the volume, we know that we can calculate moles. And once we have moles, then we can simply convert to grams using the molar mass. So let's solve for moles, and that gives us molarity times volume. So moles equals molarity times volume. This is an important relationship to recognize, and this is one that we see quite a bit and work with quite a bit in here. So remember that V is also in liters of solution, so we need to convert our volume from milliliters to liters. So 250 milliliters. There are 1,000 milliliters in 1 liter, so I'm going to divide. And that gives me 0.250 liters. Okay, now I'm going to substitute in everything into my equation here. So moles equals my molarity, which is 3.00 molar, times my volume, which is 0.250 liters, and that's 0.750 moles of potassium carbonate. I've solved for moles, but remember I was looking for mass. So now it's just one more step, converted into grams using the molar mass of potassium carbonate. The molar mass here is 138.206 grams in 1 mole. And when I multiply those things out, I'm going to get 103.655 grams. I can only keep 3 significant figures here because of my volume and my concentrations initially, so I'm going to round that to 104 grams of potassium carbonate. Okay. Example 3 is dealing with concentrations of ions. So it's important to realize that when ionic compounds dissolve, they dissociate. Dissociate is only for when I use ionic compounds. So that means they break apart into their respective ions. So the solution concentration is always given in terms of the solute before it dissolves, but it may not reflect the true composition of the solution. So for example, we'll just do this one on the side. When a solution is 1 molar NaCl, that means that we have dissolved 1 mole of solid NaCl in enough water to make 1 liter of solution. It does not mean that the solution contains 1 mole of NaCl units. If I look at my dissociation equation for that, NaCl breaks apart into 1 sodium ion, 1 sodium positive ion, and 1 chloride ion, which is negative. So the ratios here are all 1 to 1 to 1. If I have 1 mole of NaCl, that means I'm also going to have 1 mole of sodium ions and 1 mole of chloride ions. So keeping those coefficients in mind as we look at those relationships. So now let's look at our example 3 here. If I had a 0.50 molar solution of iron 3 perchlorate, what is the concentration of each ion present in solution? So let's set it up in the same way that we looked at NaCl. I want to write a dissociation equation for iron 3 perchlorate. So that's going to break apart in water, and that means I have an iron 3 plus ion, and there's only one of them, and I get 3 perchlorate ions. And now my equation is balanced, so my coefficients are 1, 1, and 3. So keeping those same relationships in mind, 0.05 molar means that I'm going to assume that I have 0.50 moles of iron 3 perchlorate in 1 liter. And that's what is going to break apart. So if I have 0.5 moles of iron 3 perchlorate, the relationship with my iron ions is 1 to 1. So I also have 0.50 moles of iron ions. But my coefficient in front of the perchlorate ions is 3, which means it's 3 times as many ions. So 0.50 times 3 is 1.50 moles of perchlorate ions. So it's important here that we get the correct balanced equations or dissociation equations to look at the right coefficients, and then it's just a relationship after that. Okay, so right now we'd like you to go back and review at the beginning what you should be able to do after watching this video.